Hello everyone, January 26th. Alright. So last night we didn't solve the problem and I got angry, which is usually how things go. So I went back to the problem, right? I went back to this problem and I started thinking, alright, so I don't think it's that hard. Let's just analyze it again, okay? And I analyze it again and I figure out what is actually going on in this problem. So basically, you have these, right? They are graphs. And what I realize is there are only two scenarios that people can sit around the table. One scenario is we have a cycle, and everybody and only those people in the cycle can be seated on the table. So if you find a cycle, that is of one possibility, and you basically try to find the biggest cycle, right? That's the one scenario. And then there's a second scenario which is depicted in this example, where you can see 0 must sit next to 0 is going to 2, 1 is also going to 2, but also 2 go to the 1. So this is a scenario where you have a cycle of size 2. Now a cycle of size 2 is very different from a cycle with larger than 2. With a cycle larger than 2, that cycle is the only one allowed on the table. But with a cycle size of 2, there is no requirement for anybody to be sitting like right next to 1 or right next to 2. So basically you can have a branch, like a very long branch leading to one end of the cycle and another branch leading into the other side of the cycle. So the problem changes, become if you find a cycle of length 2, then you want to find the longest branch that goes into each one, right? And I ran with this and it was not right because I forgot one more important piece. For any cycle of size 2, you can actually attach another cycle of size 2 with branches because it just works, right? Because there's no requirement for 2 to be next to 1. There's no requirement, right? Because there's no requirement for any of the branch to be right next to the other branch. So you can put one branch with a cycle of size 2, and you can put another branch. You can put another cycle of size 2 with branches. You can put any one of them in it. So yeah, that is it. So now the question becomes, traverse through the graph to find all the cycles, right? And at the same time, because that was how I try to do, I will find all the cycles, and at the same time, I will find the length of all the branches that leading to each cycle. Now this is a little bit tall order, and then you can see I have to explain myself really hard to kind of understand what my logic was. So like for each node, I give it a status, which I record which cycle index it belongs to, if it is part of the cycle. How much distance is this node to the cycle? If the node is inside a cycle, the distance is 0. If the node belongs to a branch, then the distance will increase as the branch gets away from the cycle. And also I need an entry point, so like at which node does the current branch insert into a cycle. So I have these three, and I use this very unsightly kind of a lot of if-else condition to build up this status array. And then once I build up the status array from this code, the next is I want to figure out all the cycles. You can see I have index and the vector. This index is the cycle index, and I have a vector. I will put all the nodes in the cycle into it. And also I need to keep track of the maximum length of the branch relative to each entry point. So here we go. We go through everything in the status, and if its cycle index logical to 0, which means it's part of a cycle, I'll put its index, put the node inside the cycle index, right, inside the cycle. And if not, which means you're part of the branch, then I'll try to find the maximum branch relative to the entry point. And once we got this all done, then I need to find the length of basically the maximum number of people you can invite with cycle of size 2 and with cycle of more than 2 size, right? So I go for this, and then like if the size is larger than 2, then we know that cycle is the only one that can be invited. So we just keep track of its maximum size. Otherwise, then for the size, this is actually just 2. I don't even have to do this. Then you need to find the branch size 1 and the branch size 2. So this is the branch size that go into one element of the cycle, so I can find the maximum length, and then the other one, right? So because you have size of 2, so you have one branch attached to one side and the other branch attached to the other side, and I find the maximum length of both, add them together, add the side which should be 2, and I got a result of 2 cycles, right? If you have a cycle of 2 and you need to add them together, like I said, any cycle of 2 can be adjacent to each other. So at the end, the result will be the maximum of the 2. Now, this is a very convoluted way of dealing with this. And then on hindsight, I think we could run the tortoise and hare algorithm, right, to find, and not necessarily, it's just, we can just DFS, right, to find all the cycles. We don't have to worry about the length, right? I don't worry about the length for now. I just go through, I just DFS to find all the cycles, right? And for each cycle of size 2, I will start from them and then try to find the longest path. But we have to reverse the favorite, right? We have to reverse it. We could call it like a parent, because I need to go backwards so that given me a size of 2, I can start from 2 going out, right? And see how far I can go, because I need to get the maximum size. So for each one, I get a maximum size. For the other one, I get maximum size. And then once that is done, I find the maximum number of people in this cycle of size 2, and I go for the other one. So it's essentially the same, but we can solve it probably faster. Now, there's one thing I do not know. That is, I don't know what the tutorial is about. And same as this one, right? I don't know the tutorial. And something I haven't read. I'm pretty sure last time when I did this, I did not solve it. I think I must have read the solution. So that was an improvement, definitely. But anyway, we're going to do today's challenge. And once we're done with this, we will go back into, oh my God. Anyway, so let's see what we have today. So it looks like another graph problem. So we have a total of num courses. You have to take label from 0 to, okay, just n minus 1. You are given an array prerequisite. So this basically is so you have to take A if you want to take B, right? So A leads to B. For example, for pair 0, 1 indicate that you have to take course 0 before you take course 1. Prerequisites can also be indirect. If course A is a prerequisite of course B, and then B is a prerequisite of course C, then course A is a prerequisite of course C. Of course, that's understandable. You are also given an array queries. For the jth query, you should answer the question whether course U is a prerequisite of course V or not. So basically, we have this graph, right? And we want to say, given any 2 nodes in the graph, tell me whether one is the parent of the other. Whether one is the parent of the other. So prerequisite, it could be, I think it's a pure, it's a full graph, right? And it's like fully graph. It could also be this, because I have there's no no restrictions on the edges. And then let's say I given this, right? If I say here and here, is this a prerequisite of this? So for each course, I have a path that goes, oh, this is like Diablo. I've been watching a lot of Diablo lately. This is like Diablo skill tree. So like for this one, let's also read the all pairs are unique. Okay. The prerequisites have no cycle. All right. So in this case, query 0 is 0. Yeah, so false and true. Yeah, this is kind of like the situation, right? So I have 1 to 2, 1 to 0, and then 2 to 0. Query 1, 0 is true. 1, 2 is also true. So how many is the number of courses? So we can technically, for each node, right? If I go from this node, that traverse, I say, give me a set of everybody that's my children. That's my descendants. Because I basically say, okay, for this course, I have, for like, in this case, for this course, all of them are my descendants. Because I have to take this in order to take this, right? So everything is my descendant. And then for this, I can say, okay, these are my descendants. And for this is my descendant. So for each one, I have descendants. And I can calculate this by joining the okay, this, the only worry for this is we might have some timeout issue happening, but I guess I don't really worry about this too much. So yeah, I got the entire my descendants for each node, and then when I query the 2, I go to 1 and I search the other one if it's in the descendant. If it is, then it's good, right? And of course, we can also do the other way around, but I think descendants is an easier idea. So now, one interesting thing is, how do we merge? Hold on, let me think one more time. So over here, I'll go, right? So I'll go this basically, if a node does not have any descendants, what does it return? It should return itself, because you are always your own descendant, right? It should return yourself. Yeah, you return yourself. Okay, so C++, what is the rule of merge two sets? Hope there is an easier way. Insert, okay. Ooh, merge two sets, okay. Or you can do union. Set union. What's C begin? What's C end? And what's this back inserter? Add elements to the end of the container C. Oh. I'm not sure. Merge? Well, how many different ways can you do? I kind of want to find a better way to do this. But set seems to be the best way. But hold a second. The number of courses is pretty low. So I can technically don't use a set. I can use a vector of size 100. I absolutely can. A true or false. Right? And then I just iterate through. Yeah, that probably is a better idea. All right, so we do need to create a graph. God, Lord, we need a graph to get the prerequisites into a graph so I can do traversal. And we need visited, right, to see which one gets visited, and we need descendants to get which one is the descendants. Still feel weird that you'll put yourself as a descendant. Let's not put yourself as descendant. Yeah, let's just return empty, which is totally fine. Okay, let's get it going. It probably will take some space, but I think it should be fine. All right, let's do this. So I need a vector of what? Boolean, right? And we call this, what do we call this? A vector of Boolean. We call this descendants. Right? Num courses to Boolean, num courses false. Right? Record each node's descendants. How do you spell descendant? Descendant. SCNDNT. All right, so we have descendants, and then we need Boolean visited. Right, num courses false. Right, I visited, and now he has to have std vector int graph num courses Alright, so we need to first convert it into a graph by saying for int, no, not int, auto. Oh, this is hard to go auto. So I0, I smaller than prerequisites of size I plus plus. I just make sure. I need to make sure that shit. I think. Oh, okay. It's still there. I accidentally turn off what I'm not supposed to turn off. Alright, so I need to make sure it does say. Yep, it's more than 100, that's fine. So we have I. Then we can have A is prerequisites I0, right? B is prerequisites I1, right? And we say graph A dot pushback B. Done, right? This we get a graph, and then we need to call a DFS. So let's put a DFS here. Or we can call void. It's fine. We don't have to return anything. DFS. We need node. We need int graph. Of course, we use a reference, and we also need vector boolean visited, and we need this is descendant. Okay. Of course, when you visit a node, it must not have been visited, or actually we should say if visited node is returned. Right, we don't do anything. If not visited, we will set it to true because I visited, and then we go through for int child of graph node. Okay. DFS child graph visited this. Okay. So once we go through all the child, then what we can say is we actually need to do a few more things, right? So if we check child or DFS child, and after we finish, we need to update my descendants. So first of all, I say descendant node child equal to true because you're my child, and then I'll say for int d of descendant child. Actually that's not right. Int I 0I smaller than descendant child, my child dot size I plus plus. So each one of my child, and if it is a true, then it will be my as well. If it's a false, so it will be an or, right? As long as one of them is true. So we say descendant node I shall all equal to descendant child I, right? If it's my child, if it's my child, then it will be my child as well. So we'll go through everything, and then at the end we return. No, wait, what? No viable overload. Why? I don't understand. There's no... I have no idea why it doesn't allow me to. Or maybe, I don't know. No viable overload. What is that? On a type that doesn't support. I don't understand. It's a Boolean value. I cannot do Boolean. I don't know. I feel like this is some. See, this one is allowed. I don't understand why it says there's no viable overload. I mean, that's. I don't understand. Well, just means I will do this. I mean, maybe I need to do. Oh, maybe this? Nope. Will this work? I have no idea why it doesn't work. But anyway, so we'll do that. And then essentially we'll say for and I0, I smaller than num courses, I plus plus. Right? And we call DFS I graph visited and then this descendants. And then we'll say std find answers. Right, for std factor of Boolean result is going to be num courses false. For auto queue of queries. Oh, that is not right. Should be queries. Might as well don't do it. Yeah, might as well don't do it. We just so queue of queries. Yeah, I think just don't do it. And then U is Q0, V is Q1. Okay. I feel like this can be the same. Say auto P of prerequisites. Right, and then we just select this P. Right, and then this is a P as well. Okay, so we have a UV, and we say if descendant U dot find no V if it's true. I can just assign this directly, right? Oh my, so I could just say res.pushback descendant Q0 Q1. So I don't even need this, and now we just return res. Alright, let's see how this one goes. I'll run it. Pretty solid, and we're gonna give it a go. (1462). So what do we call this? DFS the graph and find all the descendants of each node. Well, so prerequisites, we'll go through the prerequisites, right? And then DFS is going to be the num courses. Each one will visit once. Number of nodes. And usually I think it's U plus V and plus Q. You say where P is len prerequisite, U is num courses, V is len. Huh. Isn't that just U plus V plus Q? Right, V, U, Q is len queries. Right, that's how I understand it. Let's hope it will go as planned. So not too bad and not too good. 71 milliseconds and 4439. Oh. Alright, now time to read the tutorial. It's such interesting. I want to see, what does this say? Yeah, that was good. Alright, tree traversal on demand. Tree traversal pre-processed. Topological sort. Floyd-Warshall. And to the third. This is on demand. For each one, you just traverse. Oh, this is our solution. Ah, you can do BFS. That's true. But how do you propagate? You get a new queue, you put I in, and then you'll get the current round. Okay. Oh, for the current one, you just go through the whole thing. For the current one, you go through the whole thing. For the current one, you go through the whole thing. Makes sense. Oh man, then yeah. And then you go to the second one, you're repeatedly doing the same thing over and over again. Yeah, how does a topological sort? How you go topological sort? So you find the ones that do not have descendants. Okay. And then as it goes up, then you know that is the descendant. So you can set it. Okay. Oh, it actually makes sense. All right. So we'll start on 3. So 3 is a descendant of 2. I will go the other way around. 3 is a descendant of 2. As I remove. And 2 has an out edge. And then 0. Right, have no out edge. So 3 is descendant 2. 0 is a descendant of 2 and 1. Oh, then we have to do the other way around. So, well, this I think is better. So we find who doesn't have an in degree. Okay, who does not have an in degree? So this 1 doesn't have an in degree. So I go to 0. So 0, 2 belongs to 1. So 0 has parent 1, has parent, and 2 has parent 1. So I remove those. Now who doesn't have an in degree? Now 2 doesn't have an in degree. Okay, so we go on to, so 0 has parent 2. 3 has parent 2. Right, so that is not what I was hoping for. Zero has prerequisite 1. 2 has prerequisite 1. What in the hell? Let's just read the code. In degrees, right? So you go with in degrees, and then adjacency list is 0 to 1. Yes. Okay, so you have in degrees, and you go with the one in degree is 0. Okay. So you get the node. So you find its children. So node prerequisite adjacent insert. So the children will insert its parent. Children will insert its parent. Add node prerequisite of node to the prerequisite. So children will insert its parent. Oh, children will insert its parent. Okay. And then for prerequisite node, this I think is the way. So the children will insert its parent. Okay. And then you go to your parents prerequisite, and the children will insert your parents prerequisite. So that's how you get all the prerequisites for the children, right? And then you in degree minus minus, which is fine. Yeah, and if no in degree, so we push it in, and now you go from the children and children adjacent list. Yeah, who the children goes to, and then we look for its parent. Okay, yeah, it's the same idea. Okay, what's Floyd-Warshall again? Every possible intermediate node and checking if a path is between two nodes can be improved by going through that intermediate node and then update the shortest distance between the nodes. We just need to know if there a path exists. Oh, Floyd-Warshall is prerequisites. For edge is prerequisites is true. And then we have intermediate. So we go through every intermediate, right? And then we just see Floyd-Warshall is for this intermediate. What you want to see is from source to target, do we have a shorter distance by going through the intermediate? But in this case, we just say from source to target, do we have a path from source to intermediate, from intermediate to target? If it exists, then it's good. Floyd-Warshall. My. Good. Floyd-Warshall is pretty good. Floyd-Warshall is pretty good. Yep, it is Floyd-Warshall. It solves the problem. So given a graph, tell me whether two nodes are connected. Ooh, that is actually a good interview question. That's a very good interview question. Right? How do you do that? Right? Yeah, just give you a graph. Tell me if two nodes are connected. How would you do that? Well, you can traverse. Right, okay, yeah. Now we have like a list of queries. How can we tell it fast? Give you a query, tell me if it's, give me a query, tell me if it's this. And if we have a giant number, like the number of queries is huge, and how can we do this one fast? Yes, Floyd-Warshall is, you pre-process it and then you can just do this. Good question, good problem. I'll put this in my good interview question. All right, that'll be it for today. I don't think we have time to go back to this. Yeah, well, we'll find. There will be one day that will be an easy one, and that's when we'll do it. All right, anyway, that'll be it for today. I will see you guys tomorrow. Adios.